In this lesson, we are now going to apply what we learned in the last section in order to determine how much product we can actually produce in a lab versus how much we predict we can produce. So there are three main terms that I need to introduce you to. The first one is theoretical yield. Now the theoretical yield is what we've been working with so far. What we anticipate the mass of the product that is going to be produced will be. Better stated, it's the quantity of the product calculated to form when all of the limiting reactant is consumed. So in the problems that we did before, the mass of the product that we predicted would be formed. That is the theoretical yield. Now the theoretical yield is not going to be formed. Instead, what is actually formed in the lab is what we call the actual yield, and that is the amount of product that is actually produced. In order to calculate how successful we were in creating our product, if we're going to sit down in the lab and actually create our product and measure how much of our product we were able to make, we were able to synthesize, we use what's called percent yield. Now the percent yield is the actual yield, so what we actually got in the lab, divided by the theoretical yield, what we should have been able to produce in the lab based on how much limiting reactant we had. Now, if you multiply that by 100%, that gives you your percent yield. Unlike the previous problems that we looked at, this problem isn't actually a limiting reactant problem because you're already told which reactant limits how much product can be formed. And so it tells you that you start with 150 grams of iron 3 oxide and it's asking how much iron would be produced. So this is just a traditional stoichiometry problem in which I start with 150 grams. And what I want to do is I want to solve for grams of iron. So the first thing I need to do is I first need to convert this into moles of iron 3 oxide. And the way that I do that is that I put the molar mass of iron 3 oxide on bottom. And the molar mass of iron 3 oxide is 159.7 grams per mole. So I'm going to put that on bottom. Okay. Then I can get into moles of iron. So I'm going to put 1 mole of iron 3 oxide on bottom because the coefficient in front of iron 3 oxide is a 1. And I'm going to put 2 moles of iron up top. Now I'm in moles of iron, I just need to get into grams of iron. So I'm going to put 1 mole of iron on bottom, and then I'm going to put the molar mass of iron up top, which is 55.85 grams. And so when I calculate this, I get, once I round so that I have 3 significant figures, because this is a decimal right here, I end up with 105 grams of iron. Okay, so that's my theoretical yield. Ideally, if I start with 150 grams of iron 3 oxide, I should produce 105 grams, but as you'll notice, that's not the case. B asked me to then calculate the percent yield. Remember, the percent yield is your actual yield divided by your theoretical yield. My actual yield, what I actually got in the lab, was 87.9 grams. So I'm going to take my actual yield and I'm going to divide it by my theoretical yield, which was 105 grams. I'm going to multiply that by 100%, and that will give me my percent yield. And my percent yield in this case, rounding so it has 3 significant figures, ends up being 83.7%. So that's my percent yield.